Unit 1 Geometry, or sorry, Unit 7 Geometry Review. The first question is starting with circles. The first one, draw a central angle in it, and the second one is draw an inscribed angle. So a central angle is at the center of the circle, where the vertex of the angle is at the center of the circle. So we could say that if this point that I'm highlighting is at the center of the circle, which it doesn't look like it, but let's just say it is, then the central angle is going to be there, a central angle. An inscribed angle is made up of two chords. Chords have their endpoints on the circle. So an inscribed angle would be this case where the vertex of that angle is on the circle. If we have a central angle that measures 72 degrees, the measure of its arc is going to be the same exact thing. So arc measure and central angle measure, if we're talking about the same 2 points, then those will be equal to each other. Same thing with B. If the central angle has a measure of 21 degrees, then if the arc of that has 21 degrees, then the central angle is 21 degrees. The relationship between the inscribed angle is half the central angle, or the arc. So if we have an arc that's 140 degrees, that means our inscribed angle will be 70 degrees. And if our inscribed angle is 42 degrees, that means that our arc will be double that, so 84 degrees. On number 3, circle A has a radius of 5 and an arc length of 2 pi. And circle B has a radius of 15 and an arc length of 6 pi. I'm going to talk about the equation for arc length and sector area in just a second, but we can see here that the scale factor is times 3. Since these are just distances, arc length and radius, and they both change by the same scale factor, we can just see that the circle is dilating by 3. So that doesn't change necessarily the angle. If the arc length and the radius changed by the same factor, then the central angle should be the same. So A is false because the central angle does not split in half. The circumference of circle B is greater than the circumference of circle A by the same scale factor. Yes, so circumference is still a length. It's still just that way around the circle, that length all the way around the circle. So since the arc length changed by a factor of 3, the radius changed by a factor of 3, that means the circumference is also going to change by a factor of 3. And then C, the ratio of arc length to the radius of circle B is greater than the ratio of the arc length to the radius of circle A by the same scale factor of 3. If we just look at the first thing says of circle B, the arc length to the radius. So the arc length is 6 pi over 15. And if we compare that to the arc length of circle A over 5, these two are equal to each other. So they are actually equal to each other. So the ratio does not change because they're equal to each other. So I'm going to say this is false. If we crossed out the part about scale factor of 3, we would still say that they were equal to each other. Find the measures of angles CFE and DEF for the quadrilateral CDF that's inscribed in a circle and has a measure of 95 degrees for angle DCF and angle EDC. And that's equal to 120 degrees, 23 degrees. So if we have a circle and we have a quadrilateral in it, I'm just going to draw one to kind of imagine things. I'm going to put D here. I'm going to put C here. So that means that C, D, E, if we're going all the way around in a circle, EF will be like that. EDC is 123 degrees, and DCF is 95 degrees. So in our cyclic quadrilaterals, or quadrilaterals that can be inscribed in a circle, we talked about how opposite angles in the quadrilateral are going to be supplementary. So that means that angle DEF is going to be equal to 180 minus 95, which is equal to 85 degrees. And the other angle, angle CFE, is going to equal 180 minus 123, which is 57. So knowing that opposite angles are supplementary, we can do that. You can also go the longer route and use your inscribed angle measure with the arc and then do the other side of the circle. But this is the fastest way to do it. If line XY is tangent to the circle at point Z, that's centered at point Z, so if we have a center of point Z and it's tangent at Y, that means that that's the only place that this line is going to touch the circle. And we also have another point on the tangent line since it's line XY. Find the measure of angle ZXY. So we're finding the measure of angle ZXY. I'm going to draw. ZXY would be this angle. If we know that the measure of angle XZY is 32 degrees. Another thing that we can show is that the measure of angle XYZ is 90 degrees because this is tangent to the circle. So we know that triangles add up to 180, so that means 180 minus the 90 minus 32 will be 58. So that means angle ZXY will equal 58 degrees. Okay, a circle has a radius of 15 centimeters and a central angle of 144 degrees. Finding the area of the enclosed sector. So we have a sector area is equal to x divided by 360, x degrees, where that's the central angle measure. And since we're talking about area, we're going to do pi r squared. So if we have 144 divided by 360 times pi times 15 squared. I'm just going to take a second to calculate that. So this is 2/5 pi times 15 squared, which this is 90 pi. And since this is an area, it's going to be centimeters squared. And finding the length of the arc defined by the central angle. Arc length, so this is different than arc measure, because measure is measured by the degrees of the central angle, and arc length is measured by the distance on that arc. So arc length is going to be equal to the central angle degrees divided by 360 times 2 pi r, which is the equation for a circumference. So if we have 144 divided by 360 again times 2 pi times the 15. If we type that all in, you should get 12 pi. And since this is just a length, it's going to be in centimeters. Okay, several slices of pie are for sale. The slices of pie come wedge-shaped like areas of a circle. All the pie slices are the same height. Jolene bought a slice with a central angle of 135 degrees with a radius of 12. What's the area of the top of her pie slice? So this is the same as A in question 6. We're going to do 135 degrees divided by 360 degrees times pi times 12 squared. So 135 divided by 360 times pi times 12 squared. That equals 54 pi, and this is an area, Okay, and then the arc length is going to be 135 divided by 360 times 2 pi times r, which is 12. This is going to be equal to 9 pi centimeters. Okay, explaining the steps for each of the following. So I'm actually going to show a video of how to do this. You can look at the key for step-by-step things, but I'm going to show a video of exactly what you would need to do with a compass and a straight edge. But I'm going to do it on GeoGebra. So if you want to make a circumscribed circle with a triangle, you're first going to start by doing a perpendicular bisector. So we want to take a perpendicular bisector of at least 2 sides of the triangle. So here I'm measuring the distance from A to C and drawing that circle. And then it's centered at A, and then switching it and doing that same radius from A to C and centering at the other point C. Then we can see that we have some mistakes. That's okay. If we connect the 2 points where the circles intersect, that will create a perpendicular to the side of AC. I'm going to change the color for it so that we can see it a little bit better. So that's the perpendicular bisector of AC. We're going to do the same thing on the segment AB. So a circle around A with radius to B, circle around B with radius to A. Connect the 2 points where those circles intersect. We'll create a perpendicular bisector of side AB. And I'm going to change the color of this one so that we can see it, that is the perpendicular bisector of AB. Okay, point H, that's called the circumcenter. So at this point, we can make a circle around H that should go through A, B, and C in your triangle. And I'm turning it red to show that. It is the circumscribed circle for triangle ABC. This is the circle that's going to be going through all the vertices of the triangle. So to create a circumscribed circle, we need to create at least 2 perpendicular bisectors for edges of the triangle, segments of the triangle, and then find a circumcenter with the intersection of the 2 perpendicular bisectors. Okay, the next one is drawing a inscribed circle. So starting with an angle bisector, I'm going to angle bisector A by first drawing a circle around A so that we have 2 points along somewhere on the segments that intersect those, and then we're going to make a circle around each one that's to the radius of the other. So you can see I made a circle around D that goes to E, and then a circle around E that goes to D. The angle bisector comes from connecting the vertices with where the circles intersect. I'm going to change that color so that we can see that this is an angle bisector, so it cuts the angle in half. I'm going to do the same thing on angle C, so making 2 points, the same distance away from C, taking G, making a circle, H, making a circle with the same radius, making a line that goes through the 2 parts where those circles intersect. I'm going to change this color so we can see that it's the angle bisector. And then that is called the incenter, where J is. That's where the angle bisectors intersect. The incenter tells us, okay, that's where the circle is going to be intersecting, but now we need to create a perpendicular. So creating a perpendicular, we want to do a line perpendicular to one of the segments that goes through J. So creating a perpendicular, we're going to start with finding 2 points on one of the segments. You can see I'm doing it on AB. That's going to be K and L, and then take a circle around K to L, or circle around L going to K, And where those intersect, those two circles around K and L, that will be the perpendicular line to AB that goes through J. So that is this line right here that I'm going to turn a different color. So this green line is perpendicular. Let me just show that by drawing it. Maybe. Oh, okay. Well, cool. That's perpendicular to the segment AB. So the point where this green line intersects AB, that's going to be the radius from N to J is the radius of our inscribed circle. So if we take a circle around J going to N, I'm going to turn this a hot pink color. That is an inscribed circle. So this is around the in-center made with angle bisectors that touches the triangle at least once on each segment. And there you go. That is the Unit 7 geometry review.